Hey y'all, today we're going to be connecting equilibrium and thermochemistry. And we're going to do it by looking at how an equilibrium system will shift as the temperature changes. So let's go ahead and get started. We've already discussed the idea of Le Chatelier, where a system that is stressed will shift to reestablish equilibrium. In the past, we've always returned to the same equilibrium constant, though. When we change the temperature, we actually change the equilibrium constant itself. So it's no longer a Q versus K situation, it's old K versus new K. Let's go ahead and address how this appears, though, as it pertains to which direction the reaction will shift and what K values will then be newly established. So let's talk about the underlying reason why a reaction changes its equilibrium constant when the temperature changes. It really comes down to the idea that molecules have different energies, and Boltzmann curves are not normal distributions. So more molecules have less energy than have more energy. And because the endothermic direction of a reaction has a greater activation energy than the exothermic direction of a reaction, what ends up happening is the endothermic direction is impacted more. Because of this fact, what's going to happen is that an increase in temperature is going to speed the endothermic direction up more than it speeds up the exothermic direction, and a decrease in temperature will slow down the endothermic direction more than it slows down the exothermic direction. This means that an increase in temperature will cause the reaction to overall shift towards the endothermic direction. A decrease in temperature will cause a reaction to shift more towards the exothermic direction. It's really, really important to remember that any increase in temperature, if we think back to kinetics, is going to increase the rate of effective collisions. This means that the reaction in both directions is going to speed up. Think of this like two cars going down the highway, both going 50 miles an hour. If we increase the speed of each, so one goes up to 60, but the other one goes up to 70, the first one appears to be going slower than the second, because it is, even though both have sped up. So when we increase the temperature of any system, the forward and reverse reactions both speed up, but the endothermic reaction speeds up more. If we cool down the temperature, bring the energy down, then what happens is both forward and reverse reactions slow down, but the endothermic direction slows down more than the exothermic direction. Outside of just memorizing that an increase in temperature favors the endothermic direction and a decrease in temperature favors the exothermic direction, we can also look at this conceptually in a way that helps us. One thing to keep in mind is that energy is neither a reactant nor a product. However, just like we did back in thermochemistry with stoichiometry, we can conceptualize of energy as a reactant or a product. In an endothermic reaction, energy would be on the reactant side. On an exothermic reaction, the energy would be on the product side. But remember, it's not truly a reactant or a product. But if we think of it this way, then we can kind of go back to how we approached the Q versus K shift, where an increase in the temperature of an endothermic process would increase relatively a reactant, thereby shifting the entire process to the right towards the products. This would cause the K value to go up because our products would get higher and our reactants would become smaller. Conversely, if we decrease the temperature of an endothermic process, we would decrease the amount of a reactant. We would shift the entire process to the left towards the reactants, increasing the amount of reactant, decreasing the amount of product, and causing the K value to get smaller. So we can think of temperature or energy in this reactant product way. Just keep in mind, please, it is not a reactant nor a product. It's just a way we can conceive of it in order to make this process a little bit easier and less memorization heavy. So let's look at a practice problem where we can apply this. Here I've got an exothermic reaction. I know it's exothermic because the delta H is negative. I want to know what happens if I were to increase the temperature of this process. Now, think about it. It's exothermic. So if I'm going to think about this conceptually, the reaction is going to have energy on the product side. Okay? Because it's exothermic, energy is released from the system. If the temperatures increase, we are adding energy. Energy on the product side means we add a product, which means the entire reaction shifts towards the left to favor our reactants. The other way we can think about this is that if we have an exothermic forward direction, the reverse direction must be endothermic. An increase in temperature always favors the endothermic direction, which means that we shift towards the left, towards our reactants. So what effect would this have on the K value? Well, if we increase the temperature of this exothermic process and shift everything to the left towards the reactants, what we're going to do is decrease our K value. The K value is going to become smaller. And it's going to become smaller because our products go down, our reactants go up. All right, take a look at this problem. What would happen as a result of increasing the temperature of this system? Take a second, think about it, and when you're ready, come back and we'll talk about it. All right, so the first thing to recognize is that the forward direction of this reaction is endothermic. That means that as we increase the temperature, we favor the endothermic direction. This shifts the entire reaction to the right. So we establish a new equilibrium constant that's going to be greater in magnitude than the original. The K is going to be larger because we have shifted the entire reaction to a new equilibrium with more products and fewer reactants. More products and fewer reactants means that we have more H2 and carbon monoxide, and as a result, the answer here must be A. Remember, the carbon is a solid here, so its concentration wouldn't change, but its mass would. So we would actually have less carbon solid by mass in this system, and we would have less water in this system as a result. So that wraps up today's video. Let's do a quick recap. Today we talked about how changing the temperature of any equilibrium system creates an entirely new K value. An increase in temperature favors the direction that is endothermic. A decrease in temperature favors the direction that is exothermic. This means that it's not Q versus K, but instead is K versus new K. And so as a result, we are creating an entirely new K value as we change temperature. Today's video was written, directed, edited, and produced by Luke Maxwell and Sophia Patrick. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one. Instead of just memorying.